Well, we know that Frontier is now operational at Oak Ridge Laboratory, and they also have a machine which is called Summit, which has, I think, a rather large number, tens of thousands of GPUs. And the possibility then is that DOE machines may be used more made available for people to do these foundation models. So they've just actually, the Office of Science and Technology Policy, OSTP, and the National Science Foundation have just signed a plan for implementing what would be a shared National Artificial Intelligence Resource, NAIR, it's called. And it's a large sum of money they're requesting. And the idea is that this would democratize access to this type of training capability. And so you could use it for doing the sort of things that the CANDLE scientific data set are trying to do, but you would be able to choose what data you choose to train your system on. So that's actually, I think, now been approved. I don't know whether it's requested the money. It's not clear to me it's actually got the money, and it does depend obviously on the budget discussions. And at the moment in the US, that's a rather fraught problem because of the Republicans' refusal to extend the debt limit, and there is a possibility of the US reneging on its debts for the money it owes for what it's been doing in the last 50, 100 years. They built up a huge debt, and they have to service that debt. They owe interest payments, and they won't be able to pay and do basic things. So whether science will remain a priority, it's not clear, and we should learn in about a month. So if those of you who are interested in US politics, that's something that you need to watch for. But this is the goal that we're trying to do in the US, and there is a similar effort led by Mike Wooldridge at the Turing to try and see if we can get a similar shared resource in the UK for use by academics, but also by other organizations such as MI5 and so on. Okay, so it's important in order to be able to compete that we have some resource that people can use that can compete with what can be done by industry. Jeremy talked about the scientific machine learning benchmarks. I'd like to say a little bit about an organization called, it used to be called MLPerf, but ML Commons is what it's called now. So if I look at that, this is a community which is driven mainly by industry, and obviously people like NVIDIA like to show off that their machines, their GPUs do really well on these benchmarks. So benchmarking commercial systems is a delicate thing because obviously the companies are sensitive. So what we've been doing is leading a science working group as part of this, which actually is looking at how what benchmarks you could use for science. Should you use this network or that network, or which type of approach you can use? That's what we've been trying to do. There's a whole structure you can see. It's got lots of companies and so on. Exactly how active everybody is not clear to me, but the goal of ML Commons is to grow machine learning markets, get everybody involved, collaborative engineering and so on. And it's still, I would say, not fully delivering, but it is at least beginning to actually be potentially a very useful organization. So you might like to look at some of that in the context of BASE. And this is a slide from Jeffrey Fox, who's been leading the science working group, and we also work, there's a science working group, there's also an HPC working group, which are looking at codes that you may be familiar with, CosmoFlow DeepCam and OpenCatalyst, and those are slightly more mature than the science ones. And as you can see, the cloud masking benchmark is actually being used as an example here, and also STEM-DL, which comes from Oak Ridge. Okay, where am I? Yes, they have similar areas, benchmarkings, making the benchmarks so you can make consistent measurements about accuracy, speed, and so on in different platforms, and also how you get the result most quickly, what algorithm you should use, the data sets which you have to make. We want to make data sets available, and scientific data sets are usually easier to make available with the permission of the scientists who took the data set. So we can make the data sets open, we can make the algorithms open, and the idea is to identify best practice for doing this. And best practice data sets and benchmarks, mainly we call it ML-Perf, but it's really mainly deep learning. And what's needed is to the data sets that we have. It's not clear that they would meet the FAIR guidelines, and how you add FAIR, how you make these data sets consistent with the FAIR principles is one of the areas that we've been looking at. So I think all of the things I've talked about are the sort of things that you're beginning to look at in BASE, and I think it's very exciting that we have a project looking at exascale, and at the moment the US Department of Energy with its Advanced Scientific Computing department is looking at how it goes, what it does after now having realized exascale. What are the next steps that we should do? And they're actually currently thinking about exactly where we should go. On the way, the steps you need to take to get to zettascale. Obviously, with surrogates, you can get effectively to zettascale, but the question is, can you build machines that actually can deliver more performance than the present machines? And potentially co-design can now, where you have these chiplet models, give you the possibility of designing, instead of taking a standard off-the-shelf microprocessor, which is useful for everybody and every type of application, you can actually optimize them for particular types of applications. So those are the sort of things being discussed, but at the moment, the Advanced Scientific Department, the director has just retired, and they're just in the process of appointing a new director, and that's their challenge, is to develop the next strategy to go beyond exascale. So having listened to Jeremy and what you've been doing, I thought it would be interesting to do an advert. So this is, you can please feel free to ignore this, but I believe what there is now, was published last month, is a book which is a collection of articles. Here's the book, Artificial Intelligence for Science, and it's a collection of articles showing what people have done, what people are doing with AI, and in addition, because we've got on the whole about well over 30 applications, 30 people coming. These are some of the papers in there. This is the beginning part, setting the scene. So there's Alex Saleh, who those astronomers will know, he was behind the Sloan Digital Sky Survey, and then there's Phil Bourne, who is behind Protein Data Bank, was his original goal, but he's looking at AI in the context of data science. Then there's Janet Thornton and David Jones looking at AlphaFold, and where AlphaFold has gone, has solved essentially the old protein folding problem, but what are the implications and how it will be taken forward? Some applications of AI in astronomy, which you're also looking at. We have one Nobel Prize winner, Barry Barish, from the gravitational wave experiment, but he's looking actually at machine learning for complex instrument design and optimization. And then Jamie Sethian from Berkeley Lab is looking at how you would use AI and machine learning at the experimental facilities, looking at all the big synchrotron data, neutron source data, and data from the Stanford is now doing the same sort of things we've been doing in the at DAISY, for example. And then there's Fugaku, there's Satoshi Matsuoka and his colleagues talking about what was the first exascale supercomputer, he believes, and how you would accelerate it beyond that. And then Jayan and Arjun Shankar from Oak Ridge, Jeffrey and myself, benchmarking AI for science, which is the sort of thing we've been talking about. But I think more relevant for this particular group are the application domains. So we have, these are the application domains: astronomy and cosmology, climate change, energy, environmental science, health, life sciences, materials science and engineering, and particle physics. And there's a couple of examples in each of these, which I think would be useful for people to look at. And then how you make these data fair, there's some thoughts about that. And perspectives at the end, looking at large language models. That's a paper by Rick Stevens and Arvind Ramanathan. Autonomous vehicles, how you self-driving cars, and Ross King and his automated experiments, self-driving labs. And then a couple of more futuristic ones, Yolanda Gill looking at reflection competencies, how you actually can have the machines looking at their being self-critical, and then the difference between correlation and causation. David Heckerman, my colleague, when I was at Microsoft, is talking about the interface of machine learning and causal inference. So they're all discussed in detail, and these are some of the more experimental physics, theoretical physics, astronomy, and so on. These are the things that I heard Jeremy talk about today. So I think there may be a useful learning resource that actually people can look at. It's meant to be useful. It's not meant to be sitting on the shelf. These are the details, what it looks like. And again, it's somewhat similar. Critical infrastructure, power grids, and energy. They're looking at things like Rob Akers with fusion. This is the Princeton Fusion Lab, writing a paper. And so there are lots of examples which I think are relevant. And from that, you can actually, at the end of the book, we've actually summarized what each of these applications use, what type of networks, what type of machine learning they use. And we looked at patterns, and a reasoner, image-based, graph-based, dense systems, time generative systems, and surrogate models, for example. And you can imagine that you could have a reasoner, you could have these different science patterns, and see how they apply to these lots of applications. So you'll find a lot of information about how they've been used, how you might use them differently, and I think that they would be, it's meant to be a resource that you can actually just use. And I think the last slide is, let me just check. Yes, the last slide is merely an advert. So this is really a good value for $50. You can get an e-version, and I think it might actually be helpful for you. So get your library to get a copy, even if you don't. Okay, so I'll stop there, and I'm happy to be around for a little while longer.
Thank you, Tony.